Blackstone Audio presents The Black Hole War. My Battle with Stephen Hawking to Make the World Safe for Quantum Mechanics by Leonard Susskind. What is it that breathes fire into the equations and makes a universe for them to describe? Stephen Hawking. Introduction. There was so much to grok, so little to grok from. Robert A. Heinlein, Stranger in a Strange Land. Somewhere on the East African savanna, an aging lion spies her intended dinner. She prefers older, slower victims, but the young, healthy antelope is her only choice. The wary eyes of the prey are placed on the side of his head, ideally suited for scouring the landscape in search of dangerous predators. The predator's eyes look straight ahead, perfect for locking on to her victim and gauging the distance. This time the antelope's wide-angle scanners miss the predator, and he wanders within striking range. The powerful rear legs of the lion thrust her forward toward the panicked victim. The timeless race begins anew. Though burdened by age, the big cat is the superior sprinter. At first, the gap closes, but the lion's powerful, fast-twitch muscles gradually give way to oxygen deprivation. Soon the antelope's natural endurance wins out, and at some point the relative velocity of the cat and her prey switches sign. The closing gap begins to open. The moment she senses this reversal of fortune, Her Royal Highness is defeated. She slinks back into the underbrush. 50,000 years ago, a tired hunter spots a cave opening blocked by a boulder. A safe place to rest if he can move the heavy obstruction. Unlike his apish forebears, the hunter stands upright. In that straight-up posture, he pushes mightily against the boulder, but nothing happens. To get a better angle, the hunter places his feet at a greater distance from the rock. When his body is almost horizontal, the applied force has a much larger component in the right direction. The boulder moves. Distance? Velocity? Change of sign? Angle? Force? Component? What incredibly sophisticated calculations took place in the untutored brain of the hunter, let alone the cat? These are technical concepts that one ordinarily first meets in college physics textbooks. Where did the cat learn to gauge not only the velocity of its prey, but also, more important, the relative velocity? Did the hunter take a physics course to learn the concept of force? And trigonometry to reckon the sines and cosines for computing components? The truth, of course, is that all complex life forms have built-in, instinctive physics concepts that have been hardwired into their nervous systems by evolution. No one really knows how much is hardwired and how much is learned in early life, but the distinction is not important here. The point is that by the time our nervous systems are mature, experience, of either the personal or the evolutionary kind, has given us a lot of instinctual knowledge of how the physical world behaves. Whether hardwired or learned at a very young age, the knowledge is very difficult to unlearn. Without this pre-programmed physics software, survival would be impossible. Mutation and natural selection have made us all physicists, even animals. In humans, the large size of the brain has allowed these instincts to evolve into concepts that we carry at the conscious level. Rewiring ourselves. In fact, we're all classical physicists. The word classical refers to physics that does not require the considerations of quantum mechanics. We feel force, velocity, and acceleration at a gut level. In the science fiction novel Stranger in a Strange Land, 1961, Robert Heinlein invented a word to express this kind of deeply intuitive, almost visceral understanding of a phenomenon. Grok. Grok means to understand thoroughly and intuitively. I grok force, velocity, and acceleration. I grok three-dimensional space. I grok time and the number 5. The trajectories of a stone or a spear are grokkable, but my built-in standard-issue grokker breaks down when I try to apply it to 10-dimensional space-time, or to the number 10 to the 1,000th power, or even worse, to the world of electrons and the Heisenberg uncertainty principle. At the turn of the 20th century, a wholesale breakdown of intuition occurred. Physics suddenly found itself flummoxed by totally unfamiliar phenomena. My paternal grandfather was already 10 years old when Albert Michelson and Edward Morley discovered that the Earth's orbital motion through the hypothetical ether could not be detected. The famous experiment by Michelson and Morley was the first to show that the velocity of light does not depend on the motion of the Earth. It led to the paradoxes that Einstein eventually resolved in the special theory of relativity. The electron was unknown until he was in his 20s. He was 30 the year Albert Einstein published the special theory of relativity, and he was already well into middle age when Heisenberg discovered the uncertainty principle. There is no way that evolutionary pressure could have created an instinctive comprehension of these radically different worlds. But something in our neural networks, at least in some of us, has been primed for a fantastic rewiring that allows us not only to ask about these obscure phenomena, but also to create mathematical abstractions, deeply unintuitive new concepts, to handle and explain them. Speed created the first need to rewire. Speed so fast that it almost rivaled the velocity of an evanescent beam of light. No animal had ever moved faster than 100 miles per hour before the 20th century, and even today light travels so fast that for all but scientific purposes, it doesn't travel at all. It just appears instantaneously when the lights are switched on. Early humans had no need for hardwired circuits attuned to ultra-high speeds such as the speed of light. Rewiring for speed happened suddenly. Einstein was no mutant. He had struggled in obscurity for a decade to replace his old Newtonian wiring. But to physicists of the time, it must have seemed that a new kind of human had spontaneously appeared among them. Someone who could see the world not in terms of three-dimensional space, but in terms of four-dimensional space-time. Einstein struggled for another decade, this time in plain view of physicists, to unify what he had called special relativity with Newton's theory of gravity. What emerged, the general theory of relativity, profoundly changed all the traditional ideas about geometry. Space-time became flexible, curved, or warped. It responded to the existence of matter almost like a sheet of rubber under stress. Previously, space-time had been passive, its geometric properties fixed. In the general theory, space-time became an active player. It could be deformed by massive objects such as planets and stars, but it could not be visualized, not without a lot of additional mathematics anyway. In 1900, 5 years before Einstein appeared on the scene, another much weirder paradigm shift was set in motion with the discovery that light is composed of particles called photons, or sometimes light quanta. The term photon was not used until 1926 when the chemist Gilbert Lewis coined it. The photon theory of light was only a hint of the revolution to come. The mental gymnastics would be far more abstract than anything yet seen. Quantum mechanics was more than a new law of nature. It involved changing the rules of classical logic, the ordinary rules of thought that every sane person uses to make deductions. It seemed crazy. But crazy or not, physicists were able to rewire themselves with a new logic called quantum logic. In Chapter 4, I will explain everything you need to know about quantum mechanics. Be prepared to be mystified by it. Everyone is. Relativity and quantum mechanics have been reluctant companions from the beginning. As soon as they were brought together in a shotgun wedding, violence broke out, the mathematics unleashing furious infinities for every question a physicist could ask. It took half a century for quantum mechanics and special relativity to be reconciled, but eventually the mathematical inconsistencies were eliminated. By the early 1950s, Richard Feynman, Julian Schwinger, Shinichiro Tominaga, and Freeman Dyson had laid the groundwork for a synthesis of special relativity and quantum mechanics called quantum field theory. In 1965, Feynman, Schwinger, and Tominaga received the Nobel Prize for their work, but the modern way of thinking about quantum field theory owes as much to Dyson as to the others. But the general theory of relativity, Einstein's synthesis of special relativity and Newton's theory of gravity, and quantum mechanics remained irreconcilable, though not from lack of trying. Feynman, Steven Weinberg, Bryce DeWitt, and John Wheeler all attempted to quantize Einstein's gravity equations, but all that came out was mathematical rubbish. Perhaps that was not surprising. Quantum mechanics ruled the world of very light objects. Gravity, by contrast, seemed important for only very heavy lumps of matter. It seemed safe to assume that nothing was light enough for quantum mechanics to be important, and also heavy enough for gravity to be important. As a result, many physicists throughout the second half of the 20th century considered the pursuit of such a unifying theory to be worthless, fit only for crackpots and philosophers. But others thought this was a myopic view. For them, the idea of two incompatible, even contradictory, theories of nature was intellectually intolerable. They believed that gravity almost surely played a role in determining the properties of the smallest building blocks of matter. The problem was that physicists had not probed deeply enough. Indeed, they were correct. Down in the basement of the world, where distances are far too small to be directly observed, nature's smallest objects exert powerful gravitational forces on one another. Today, it is widely believed that gravity and quantum mechanics will play equally important roles in determining the laws of elementary particles. But the size of nature's basic building blocks is so inconceivably small that no one should be surprised if a radical rewiring will be needed to understand them. The new wiring, whatever it is, will be called quantum gravity. But even without knowing its detailed form, we can safely say that the new paradigm will involve very unfamiliar concepts of space and time. The objective reality of points of space and instants of time is on its way out. Going the way of simultaneity, one of the first things to go with the 1905 relativity revolution was the idea that two events can objectively be simultaneous. Determinism is the principle that the future is completely determined by the past. According to quantum mechanics, the laws of physics are statistical, and nothing can be predicted with certainty. And the dodo. Quantum gravity describes a much more subjective reality than we ever imagined. As we will see in Chapter 18, it is a reality that in many ways is like the ghostly three-dimensional illusion cast by a hologram. Theoretical physicists are struggling to gain a foothold in a strange land. As in the past, thought experiments have brought to light paradoxes and conflicts between fundamental principles. This book is about an intellectual battle over a single thought experiment. In 1976, Stephen Hawking imagined throwing a bit of information, a book, a computer, even an elementary particle, into a black hole. Black holes, Hawking believed, were the ultimate traps, and the bit of information would be irretrievably lost to the outside world. This apparently innocent observation was hardly as innocent as it sounds. It threatened to undermine and topple the entire edifice of modern physics. Something was terribly out of whack. The most basic law of nature, the conservation of information, was seriously at risk. To those who paid attention, either Hawking was wrong, or the 300-year-old center of physics wasn't holding. At first, very few people paid attention. For almost 2 decades, the controversy took place largely below the radar. The great Dutch physicist Gerard 't Hooft and I were an army of 2 on one side of the intellectual divide. Stephen Hawking and a small army of relativists were on the opposite side. It was not until the early 1990s that most theoretical physicists, especially string theorists, woke up to the threat that Hawking had posed. And then they mostly got it wrong. Wrong for a while, anyway. The Black Hole War was a genuine scientific controversy. Nothing like the pseudo-debates over intelligent design or the existence of global warming. Those phony arguments cooked up by political manipulators to confuse a naive public don't reflect any real scientific differences of opinion. By contrast, the split over black holes was very real. Eminent theoretical physicists could not agree on which principles of physics to trust and which to give up. Should they follow Hawking with his conservative views of space-time, or 't Hooft and myself with our conservative views of quantum mechanics? Every point of view seemed to lead only to paradox and contradiction. Either space-time, the stage on which the laws of nature play out, could not be what we thought it was, or the venerable principles of entropy and information were wrong. Millions of years of cognitive evolution and a couple of hundred years of physics experience once again had fooled us, and we found ourselves in need of new mental wiring. The Black Hole War is a celebration of the human mind and its remarkable ability to discover the laws of nature. It is an explanation of a world far more remote to our senses than quantum mechanics and relativity. Quantum gravity deals with objects 100 billion times smaller than a proton. We have never directly experienced such small things, and we probably never will. But human ingenuity has allowed us to deduce their existence, and surprisingly, the portals into that world are objects of huge mass and size. Black holes. The Black Hole War is also a chronicle of a discovery. The holographic principle is one of the most unintuitive abstractions in all of physics. It was the culmination of more than 2 decades of intellectual warfare over the fate of information that falls into a black hole. It was not a war between angry enemies. Indeed, the main participants are all friends. But it was a fierce intellectual struggle of ideas between people who deeply respected each other, but also profoundly disagreed. There is a widespread opinion that needs to be dispelled. The public image of physicists, especially theoretical physicists, is often one of nerdy, narrow people whose interests are alien, non-human, and boring. Nothing could be further from the truth. The great physicists I have known, and there have been many of them, are extremely charismatic people with powerful passions and fascinating minds. The diversity of personalities and ways of thinking is endlessly interesting to me. Writing about physics for a general audience without including the human element seems to me to leave out something interesting. In writing this book, I have tried to capture some of the emotional side of the story as well as the scientific side. A note about big numbers and small numbers. Throughout this book, you will find lots of very big and very small numbers. The human brain was not constructed to visualize numbers much bigger than 100 or much smaller than 1/100th, but we can train ourselves to do better. For example, being very used to dealing with numbers, I can more or less picture a million, but the difference between a trillion and a quadrillion is beyond my powers of visualization. Many of the numbers in this book are far beyond trillions and quadrillions. How do we keep track of them? The answer involves one of the greatest rewiring feats of all time: the invention of exponents and scientific notation. Let's begin with a fairly big number. The population of the Earth is about 6 billion. 1 billion is 10 multiplied by itself 9 times. It can also be expressed as 1 followed by 9 zeros. 1 billion equals 10 times 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 10 equals 1 billion. A shorthand notation for 10 multiplied by itself 9 times is 10 to the 9th power. Thus, the Earth's population is roughly given by this equation. 6 billion equals 6 times 10 to the 9th power. In this case, 9 is called the exponent. Here is a much bigger number: the total number of protons and neutrons in the Earth. Number of protons and neutrons in Earth, approximately, equals 5 times 10 to the 51st power. That's obviously a lot bigger than the number of people on Earth. How much bigger? 10 to the 51st power has 51 factors of 10, but 1 billion has only 9. So 10 to the 51st power has 42 more factors of 10 than 10 to the 9th power. That makes the number of nuclear particles in the Earth about 10 to the 42nd power times bigger than the number of people. Notice that I've ignored the multipliers 5 and 6 in the previous equations. 5 and 6 are not very different from each other, so if you just want a rough order of magnitude estimate, you can ignore them. Let's take 2 really big numbers. The total number of electrons in the portion of the universe that we can see with the most powerful telescopes is about 10 to the 80th power. The total number of photons, don't confuse photons with protons. Photons are particles of light. Protons, together with neutrons, make up the atomic nucleus, is about 10 to the 90th power. Now, 10 to the 90th power may not sound so much bigger than 10 to the 80th power, but that's deceptive. 10 to the 90th power is 10 to the 10th power times bigger, and 10 billion is a very big number. In fact, 10 to the 80th power and 10 to the 81st power look almost the same. But the second number is 10 times bigger than the first. So a modest change in the exponent can mean an enormous change in the number it represents. Now let's consider very small numbers. The size of an atom is about 1/10 billionth of a meter. A meter is about a yard. In decimal notation, size of atom equals 1/10 billionth meters. Note that the 1 appears in the 10th decimal place. Scientific notation for 1/10 billionth involves a negative exponent, namely -10. 1/10 billionth equals 10 to the negative 10th power. Numbers with negative exponents are small, and numbers with positive exponents are large. Let's do one more small number. Elementary particles, such as the electron, are very light compared to ordinary objects. A kilogram is the mass of a liter, roughly a quart, of water. The mass of an electron is vastly smaller. In fact, the mass of a single electron is about 9 times 10 to the negative 31st power kilograms. Finally, multiplying and dividing is very easy in scientific notation. All you have to do is add or subtract the exponents. Here are some examples. 10 to the 51st power equals 10 to the 42nd power times 10 to the 9th power. 10 to the 81st power divided by 10 to the 80th power equals 10. 10 to the negative 31st power times 10 to the 9th power equals 10 to the negative 22nd power. Exponents aren't the only shorthand people use to describe immensely large numbers. Some of these numbers have their own names. For example, a googol is 10 to the 100th power, 1 followed by 100 zeros. And a googolplex is 10 to the power of googol, 1 followed by a googol zeros, a tremendously bigger number. With these basics out of the way, let's turn to the somewhat less abstract world. In this case, San Francisco, 3 years into President Ronald Reagan's first term, the Cold War at fever pitch, and a new war about to begin. Part 1. The Gathering Storm. History will be kind to me, for I intend to write it. Winston Churchill. The titles of the first and fourth parts of this book are taken from the first and fifth volumes of Churchill's History of World War II. Chapter 1. The First Shot. San Francisco, 1983. The dark clouds of war had been gathering for more than 80 years by the time the initial skirmish took place in the attic of Jack Rosenberg's San Francisco mansion. Jack, also known as Werner Erhard, was a guru, a super salesman, and a bit of a con man. Prior to the early 1970s, he had been just plain Jack Rosenberg, encyclopedia salesman. Then one day, while crossing the Golden Gate Bridge, he had an epiphany. He would save the world and, while he was at it, make a huge fortune. All he needed was a classier name and a new pitch. His new name would be Werner, for Werner Heisenberg, Erhard, for the German statesman Ludwig Erhard. The new pitch would be Erhard Seminars Training, a.k.a. EST. And he did succeed, if not in saving the world, at least in making his fortune. Thousands of shy, insecure people paid several $100s each to be harangued, harassed, and, according to legend, told that they couldn't go to the toilet during the 16-hour motivational seminars run by Werner or one of his many disciples. It was a lot cheaper and faster than psychotherapy, and in a way it was effective. Shy and uncertain going in, the attendees appeared confident, strong, and friendly, just like Werner, coming out. Never mind that they sometimes seemed like manic handshaking robots. They felt better. The training was even the subject of a very funny movie called Semi-Tough with Burt Reynolds. EST groupies surrounded Werner. Slaves would definitely be too strong a term. Let's call them volunteers. There were EST-trained chefs to cook his food, chauffeurs to drive him around town, and all manner of house servants to staff his mansion. But ironically, Werner himself was a groupie. A physics groupie. I liked Werner. He was smart, interesting, and fun, and he was fascinated by physics. He wanted to be part of it, so he spent wads of money bringing groups of elite theoretical physicists to his mansion. Sometimes just a few of his special physics buddies, Sidney Coleman, David Finkelstein, Dick Feynman, and I, would meet in his home for spectacular dinners catered by celebrity chefs. But more to the point, Werner liked to host small, elite conferences. With a well-equipped seminar room in the attic, a staff of volunteers to cater to our every whim, and San Francisco as the venue, the mini-conferences were lots of fun. Some physicists were suspicious of Werner. They thought he would use the physics connection in some devious way to promote himself, but he never did. As far as I can tell, he just liked hearing about the latest ideas from the characters who were hatching them. I think there were 3 or 4 EST conferences altogether, but only one left an indelible imprint on me and on my physics research. The year was 1983. The guests included, among other notables, Murray Gell-Mann, Sheldon Glashow, Frank Wilczek, Savas Dimopoulos, and Dave Finkelstein. But for this story, the most important participants were the 3 main combatants in the Black Hole War: Gerard 't Hooft, Stephen Hawking, and myself. Although I had met Gerard only a few times before 1983, he had made a big impression on me. Everyone knew that he was brilliant, but I sensed much more than that. He seemed to have a steel core, an intellectual toughness that exceeded that of anyone else I knew, with the possible exception of Dick Feynman. Both of them were showmen. Dick was an American showman, brash, irreverent, and full of macho one-upmanship. Once, among a group of young physicists at Caltech, he described a joke that the graduate students had played on him. There was a sandwich place in Pasadena where they served celebrity sandwiches. You could get a Humphrey Bogart, a Marilyn Monroe, and so on. The students had taken him to lunch there, I think for his birthday, and one after another ordered the Feynman sandwich. They had conspired with the manager beforehand, and the guy behind the counter didn't bat an eye. After he finished the story, I said, "Gee, Dick, I wonder what the difference would be between a Feynman sandwich and a Susskind sandwich." "Oh, they'd be about the same," he replied, "except the Susskind sandwich would have more ham." "Yeah," I responded, "but a lot less bologna." That was probably the only time I beat him at that game. Gerard is a Dutchman. The Dutch are the tallest people in Europe, but Gerard is short and solidly built, with a mustache and the look of a burgher. Like Feynman, 't Hooft has a strong competitive streak, but I am sure that I never got the better of him. Unlike Feynman, he is a product of old Europe, the last great European physicist, inheritor of the mantle of Einstein and Bohr. Although he is 6 years younger than I am, I was in awe of him in 1983, and rightfully so. In 1999, he was awarded the Nobel Prize for his work leading to the Standard Model of elementary particles. But it wasn't Gerard whom I most remember from Werner's attic. It was Stephen Hawking, whom I first met there. It's where Stephen dropped the bomb that set the Black Hole War in motion. Stephen is also a showman. He's a physically tiny man. I doubt that he weighs 100 pounds, but his small body contains a prodigious intellect and an equally outsized ego. At that time, Stephen was in a more or less ordinary powered wheelchair, and he could still talk using his own voice, though he was very hard to understand unless you spent a lot of time with him. He traveled with an entourage that included a nurse and a young colleague who would listen to him very carefully and then repeat what he said. In 1983, his translator was Martin Rosek, now a well-known physicist and one of the pioneers in an important subject called supergravity. At the time of the EST conference, however, Martin was quite young and not so well known. Nevertheless, from previous meetings, I knew that he was a very capable theoretical physicist. At some point in our conversation, Stephen, through Martin, said something that I thought was wrong. I turned to Martin and asked him for clarification of the physics. He looked at me like a deer caught in the headlights. Later he told me what had happened. It seems that translating Stephen's speech required such intense concentration that he was usually unable to keep track of the conversation. He barely knew what we were talking about. Stephen is an unusual sight. I'm not talking about his wheelchair or the obvious physical limitations of his body. Despite the immobility of his facial muscles, his faint smile is unique, simultaneously angelic and devilish, projecting a sense of secret amusement. During the EST conference, I found talking to Stephen very difficult. It took a long time for him to answer, and his answers were usually very brief. These short, sometimes single-word answers, his smile, and his almost disembodied intellect were unnerving. It was like communicating with the oracle at Delphi. When someone submitted a question to Stephen, the initial response was absolute silence, and the eventual output was often incomprehensible. But the knowing smile said, "You may not understand what I'm saying, but I do, and I am right." The world sees the diminutive Stephen as a mighty man, a hero of extraordinary courage and fortitude. Those who know him see other sides, Stephen the playful and Stephen the bold. One evening during the EST conference, a few of us were out walking on one of San Francisco's famous break-busting hills. Stephen was with us, driving his powered chair. When we reached the steepest section, he turned on the devilish smile. Without a moment's hesitation, he took off down the hill at maximum velocity, the rest of us startled. We chased him, fearing the worst. When we got to the bottom, we found him sitting and smiling. He wanted to know whether there was a steeper hill to try. Stephen Hawking, the Evel Knievel of physics. Indeed, Hawking is very much a daredevil of a physicist, but perhaps his boldest move ever was the bomb he dropped in Werner's attic. I can't remember how his lecture worked at EST. Today, a physics seminar given by Stephen has him sitting quietly in his chair while a disembodied computer voice lectures from a previous recording. That computerized voice has become Stephen's trademark. As flat as it is full of personality and humor. But back then, maybe he talked and Martin translated. However it happened, the bomb fell with full force on Gerard and me. Stephen claimed that information is lost in black hole evaporation, and worse, he seemed to prove it. If that was true, Gerard and I realized, the foundations of our subject were destroyed. How did the rest of the people in Werner's attic receive the news? Like the coyote in the Roadrunner cartoon who overruns the edge of the cliff. The ground had disappeared beneath their feet, but they didn't know it yet. It is said of cosmologists that they are often in error, but never in doubt. If so, Stephen is only half a cosmologist, never in doubt, but hardly ever wrong. In this case, he was. But Stephen's mistake was one of the most seminal in the history of physics and could ultimately lead to a profound paradigm shift about the nature of space, time, and matter. Stephen's lecture was the last that day. For about an hour afterward, Gerard stood glaring at the diagram on Werner's blackboard. Everyone else had left. I can still see the intense frown on Gerard's face and the amused smile on Stephen's. Almost nothing was said. It was an electric moment. On the blackboard was a Penrose diagram, a type of diagram representing a black hole. The horizon, the edge of the black hole, was drawn as a dashed line, and the singularity at the center of the black hole was an ominous-looking jagged line. Lines pointing inward through the horizon represented bits of information falling past the horizon into the singularity. There were no lines coming back out. According to Stephen, those bits were irretrievably lost. To make matters worse, Stephen had proved that black holes eventually evaporate and disappear, leaving no trace of what has fallen in. Stephen's theory went even further. He postulated that the vacuum, empty space, was full of virtual black holes that flashed into and out of existence so rapidly that we didn't notice them. The effect of these virtual black holes, he claimed, was to erase information, even if there was no real black hole in the vicinity. In Chapter 7, you will learn exactly what information means, and also what it means to lose it. For now, just take it from me, this was an unmitigated disaster. 't Hooft and I knew it, but the response from everyone else who heard about it that day was, ho-hum, information is lost in black holes. Stephen himself was sanguine. For me, the toughest part of dealing with Stephen has always been the irritation I feel at his complacency. Information loss was something that just could not be right. But Stephen couldn't see it. The conference broke up, and we all went home. For Stephen and Gerard, that meant back to Cambridge University and the University of Utrecht, respectively. For me, a 40-minute drive south on Route 101 back to Palo Alto and Stanford University. It was hard to concentrate on the traffic. It was a cold day in January, and every time I stopped or slowed down, I would draw the figure from Werner's blackboard on my frosty windshield. Back at Stanford, I told my friend Tom Banks about Stephen's claim. Tom and I thought about it intensely. To try to learn some more, I even invited one of Stephen's former students to come up from Southern California. We were very suspicious of Stephen's claim, but for a while we weren't sure why. What's so bad about losing a bit of information inside a black hole? Then it dawned on us. Losing information is the same as generating entropy, and generating entropy means generating heat. The virtual black holes that Stephen had so blithely postulated would create heat in empty space. Together with another colleague, Michael Peskin, we made an estimate based on Stephen's theory. We found that if Stephen was right, empty space would heat up to 1,000 billion degrees in a tiny fraction of a second. Although I knew that Stephen was wrong, I couldn't find the hole in his reasoning. Perhaps that was what irritated me the most. The ensuing black hole war was more than an argument between physicists. It was also a war of ideas, or perhaps a war between fundamental principles. The principles of quantum mechanics and those of general relativity always seemed to be fighting each other, and it was not clear that the two could coexist. Hawking is a general relativist who had put his trust in Einstein's equivalence principle. 't Hooft and I are quantum physicists who felt certain that the laws of quantum mechanics could not be violated without destroying the foundations of physics. In the next 3 chapters, I will set the stage for the black hole war by explaining the basics of black holes, general relativity, and quantum mechanics. Chapter 2. The Dark Star. There are more things in heaven and earth, Horatio, than are dreamt of in your philosophy. William Shakespeare, Hamlet. The earliest glimpse of anything like a black hole came in the late 18th century, when the great French physicist Pierre-Simon de Laplace and the English cleric John Michel had the same remarkable thought. All physicists in those days were intensely interested in astronomy. Everything that was known about astronomical bodies was known by the light they emitted, or, in the case of the moon and planets, the light they reflected. In Michel and Laplace's time, Isaac Newton, though dead for half a century, was by far the most powerful influence in physics. Newton believed that light was composed of tiny particles. Corpuscles, he called them. And if so, why wouldn't light be affected by gravity? Laplace and Michel wondered whether there could be stars so massive and dense that light could not escape their gravitational pull. Wouldn't such stars, if they existed, be completely dark and therefore invisible? The American Heritage Dictionary of the English Language, 4th edition, defines a projectile as a fired, thrown, or otherwise propelled object, such as a bullet, having no capacity for self-propulsion. Could a projectile be a single particle of light? According to Michel and Laplace, the answer was yes. Can a projectile, a stone, a bullet, or even an elementary particle, ever escape the gravitational pull of a mass such as the Earth? In one sense, yes, and in another sense, no. The gravitational field of a mass never ends. It goes on forever, getting weaker and weaker with increasing distance. Thus, a projectile can never completely escape the Earth's gravity. But if a projectile is thrown upward with a large enough velocity, it will continue its outward motion forever. the diminishing gravity being too weak to turn it around and pull it back down to the surface. That is the sense in which a projectile can escape the Earth's gravity. The strongest human has no chance of throwing a rock into outer space. A professional baseball pitcher might achieve a vertical throw of 75 yards, about 1/4 the height of the Empire State Building. Ignoring air resistance, a pistol can fire a bullet to a height of about 3 miles. But there is a certain velocity, naturally called the escape velocity, which is just barely enough to launch an object onto an eternal outbound trajectory. Starting with anything less than the escape velocity, a projectile will fall back to the Earth. Starting with a greater velocity, the projectile will escape to infinity. The escape velocity from the surface of the Earth is a mighty 25,000 miles per hour. The escape velocity is an idealization that ignores effects such as air resistance, which would require the object to have a far greater velocity. For the moment, let's refer to any massive astronomical body as a star, whether it's a planet, an asteroid, or a true star. The Earth is just a small star, the Moon an even smaller star, and so on. According to Newton's law, the gravitational influence of a star is proportional to its mass, so it's entirely natural that the escape velocity should also depend on the star's mass. But mass is only half the story. The other half has to do with the star's radius. Imagine that as you stand on the surface of the Earth, some force begins to squeeze the Earth to a smaller size, but without it losing any of its mass. If you were standing on the surface of the Earth, the compression would move you closer to each and every atom of the Earth. As you moved closer to the mass, the effect of gravity would become more powerful. Your own weight, a function of gravity, would increase, and, as you might expect, it would become harder to escape the Earth's pull. This illustrates one fundamental rule of physics. Shrinking a star without losing any mass increases the escape velocity. Now imagine exactly the opposite situation. For some reason, the Earth expands, so that you move away from the mass. Gravity at the surface would become weaker and therefore easier to escape. The question that Michel and Laplace asked was whether a star could have such large mass and small size that the escape velocity would exceed the speed of light. When Michel and Laplace first had this prophetic thought, the speed of light, denoted by the letter c, had been known for more than 100 years. The Danish astronomer Ole Rømer had determined c in 1676 and had found that light travels with the stupendous velocity of 186,000 miles, or 7 times around the Earth, per second. In metric units, the speed of light is about 3 times 10 to the 8th power meters per second. c equals 186,000 miles per second. With that enormous speed, it would take an extremely large or extremely concentrated mass to trap light, but there was no obvious reason why it couldn't happen. Michel's paper to the Royal Society was the first reference to the objects that John Wheeler would later call black holes. It may surprise you to know that as forces go, gravity is extremely weak. A weightlifter or high jumper may feel differently, but a simple experiment shows just how feeble gravity is. Begin with a light weight. A small ball of styrofoam works well. By one means or another, electrically charge the weight with some static electricity. Rubbing it against your sweater should work. Now, hang it from the ceiling by a thread. When it stops swinging, the thread will hang vertically. Next, bring a second, similarly charged object near the hanging weight. The electrostatic force will push the suspended weight and make the thread hang at an angle. The same thing can be done with a magnet if the hanging weight is made of iron. Now get rid of the electric charge and the magnet and attempt to deflect the small weight by bringing a very heavy mass up close. The gravitational pull of that heavy mass will pull on the hanging weight, but the effect will be far too small to detect. Gravity is extremely feeble by comparison with electric and magnetic forces. But if gravity is so weak, why can't we jump to the moon? The answer is that the huge mass of the Earth, 6 times 10 to the 24th power kilograms, easily compensates the weakness of gravity. But even with that mass, the escape velocity from the Earth's surface is less than 1/10,000th of the speed of light. The dark star of Michel's and Laplace's imaginations would have to be tremendously massive and tremendously compressed if the escape velocity were to be greater than c. Just to give you a feel for the magnitudes involved, let's look at the escape velocities from a few astronomical objects. Escaping from the Earth's surface requires an initial velocity of about 8 miles, about 11 kilometers per second, which, as I said, is about 25,000 miles per hour. By terrestrial standards, that's very fast, but compared to the speed of light, it's a slow crawl. You would have a much better chance of escaping from an asteroid than from the Earth. An asteroid with a radius of 1 mile has an escape velocity of about 6 feet, 2 meters per second, an easy jump. By contrast, the Sun is much bigger than the Earth in both radius and mass. The mass of the Sun is about 2 times 10 to the 30th power kilograms. That's about 500,000 times the mass of the Earth. The Sun's radius is about 700,000 kilometers, or about 100 times the Earth's radius. These two things work against each other. The larger mass makes it more difficult to escape from the Sun's surface, while the larger radius makes it easier. The mass wins, however, and the escape velocity from the Sun's surface is about 50 times greater than from the Earth's surface. That's still very much slower than the speed of light. The Sun is not fated to remain the same size forever, however. Eventually, when a star runs out of fuel, the outward pressure caused by its internal heat fails. Like a giant vice, gravity begins to crush the star to a small fraction of its original size. About 5 billion years from now, the Sun will be exhausted, and it will collapse to what is known as a white dwarf, with a radius about the same as the Earth's. Escaping from its surface will require a velocity of 4,000 miles per second. Fast, but still only 2% of the speed of light. If the Sun were just a bit heavier, about 1.5 times its actual value, the additional mass would crush it right past the white dwarf stage. The electrons in the star would be squeezed into the protons to form an incredibly dense ball of neutrons. A neutron star is so dense that just a single teaspoon of the stuff would weigh more than 10 trillion pounds. But a neutron star is not yet a dark star. The escape velocity from its surface would be close to the speed of light, about 80% of c, but not quite there. If the collapsing star were even heavier, say about 5 times the Sun's mass, even the dense neutron ball would no longer be able to withstand the inward pull of gravity. In an ultimate implosion, it would be crushed to a singularity, a point of almost infinite density and destructive power. The escape velocity from that tiny core would be far beyond the speed of light. Thus, a dark star, or as we would say today, a black hole, would be born. Einstein so disliked the idea of black holes that he dismissed their possibility, claiming that they could never form. But whether Einstein liked them or not, black holes are real. Astronomers today routinely study them, not only in the form of single collapsed stars, but also in the centers of galaxies, where millions and even billions of stars have coalesced into black giants. The Sun is not heavy enough to compress itself into a black hole, but if we could help it along by squeezing it in a cosmic vice to a radius of just 2 miles, it would become a black hole. You might think that it would spring back to a 5-mile radius if the pressure of the vice were relaxed, but by then, it would be too late. The material of the Sun would have gone into a kind of free fall. The surface would have quickly passed the 1-mile point, the 1-foot point, and the 1-inch point. There would be no stopping it until it formed a singularity, and that awful implosion would be irreversible. Imagine that we found ourselves near a black hole, but at some point well away from the singularity. Would light, starting from that point, escape the black hole? The answer depends on both the mass of the black hole and exactly where the light began its journey. An imaginary sphere called the horizon divides the universe in two. Light that starts inside the horizon will inevitably get pulled back into the black hole, but light that starts outside the horizon can escape the black hole's gravity. If the sun were ever to become a black hole, the radius of the horizon would be about 2 miles. The radius of the horizon is called the Schwarzschild radius. It was named for the astronomer Karl Schwarzschild, who was the first to study the mathematics of black holes. The Schwarzschild radius depends on the mass of the black hole. In fact, it is directly proportional to the mass. For example, if the sun's mass were replaced by 1,000 solar masses, a light ray starting 2 or 3 miles away would have no chance of escaping, because the radius of the horizon would increase 1,000-fold to 2,000 miles. The proportionality between mass and the Schwarzschild radius is the first fact that a physicist learns about black holes. The Earth is approximately 1,000,000 times less massive than the Sun, so its Schwarzschild radius is 1,000,000 times smaller than the Sun's. It would have to be squeezed to about the size of a cranberry to make a dark star. By contrast, lurking at the center of our galaxy is a supersized black hole with a Schwarzschild radius of about 100 million miles, about the size of the Earth's orbit around the Sun. And in other pockets of the universe, there are even bigger monsters than that. No place is as nasty as the singularity of a black hole. Nothing can survive its infinitely powerful forces. Einstein was so appalled by the idea of a singularity that he rebelled against it. But there was no way out. If enough mass piles up, nothing can withstand the overwhelming pull toward the center. Tides and the 2,000-mile man. What causes the seas to rise and fall as if they were breathing 2 big breaths every day? It's the moon, of course. But how does it do it? And why twice a day? I will explain, but first let me tell you about the fall of the 2,000-mile man. Imagine the 2,000-mile man, a giant who measures 2,000 miles from the tip of his head to the bottoms of his feet, as he falls, feet first, from outer space toward the Earth. Far out in outer space, gravity is weak, so weak that he feels nothing. But as he gets closer to the Earth, strange sensations arise in his long body. Sensations not of falling, but of being stretched. The problem is not the giant's overall acceleration toward the Earth. The cause of his discomfort is that gravity is not uniform throughout space. Far from the Earth, it is almost entirely absent. But as he draws closer, the pull of gravity increases. For the 2,000-mile man, this presents difficulties even while he is in free fall. The poor man is so tall that the pull on his feet is much stronger than the pull on his head. The net effect is an uncomfortable feeling that his head and feet are being pulled in opposite directions. Perhaps he can avoid being stretched by falling in a horizontal position, legs and head at the same altitude. Yet when the giant tries it, he finds a new discomfort. The stretching sensation is replaced by an equal feeling of compression. He feels as if his head is being pressed toward his feet. To understand why this is so, let's temporarily imagine that the Earth is flat. Here is what it would look like. Imagine vertical lines together with arrows indicating the direction of the gravitational force, not surprisingly straight down. But more than that, the strength of the gravitational pull is entirely uniform. The 2,000-mile man would have no trouble in this environment, whether he fell vertically or horizontally. Not until he hit the ground, anyway. But the Earth is not flat. Both the strength and the direction of gravity vary. Instead of pulling in a single direction, gravity pulls directly toward the center of the planet. This creates a new problem for the giant if he falls horizontally. The force on his head and feet will not be the same because gravity, as it pulls toward the center of the Earth, will push his head toward his feet, leading to the strange sensation of being compressed. Let's return to the question of the ocean tides. The cause of the twice-daily rising and falling of the seas is exactly the same as the cause of the 2,000-mile man's discomfort, the non-uniformity of gravity. But in this case, it's the moon's gravity, not the Earth's. The moon's pull on the oceans is strongest on the side of the Earth facing the moon and weakest on the far side. You might expect the moon to create a single oceanic bulge on the closer side, but that's wrong. For the same reason that the tall man's head is pulled away from his feet, the water on both sides of the earth, near and far, bulges away from it. One way to think about this is that on the near side, the moon pulls the water away from the earth, but on the far side, it pulls the earth away from the water. The result is two bulges on opposite sides of the earth, one facing toward the moon and the other facing away. As the earth turns one revolution under the bulges, each point experiences two high tides. The distorting forces caused by variations in the strength and direction of gravity are called tidal forces, whether they are due to the moon, earth, sun, or any other astronomical mass. Can humans of normal size feel tidal forces, for example, when jumping from a diving board? No, we cannot, but only because we are so small that the Earth's gravitational field hardly varies across the length of our bodies. Descent into Hell. I entered on the deep and savage way. Dante, The Divine Comedy. Tidal forces would not be so benign if you fell toward a solar mass black hole. All that mass compacted into the tiny volume of the black hole not only makes gravity very strong near the horizon, but it also makes it very non-uniform. Well before you arrived at the Schwarzschild radius, when you were more than 100,000 miles from the black hole, tidal forces would become quite uncomfortable. Like the 2,000-mile man, you would be too big for the rapidly varying gravitational field of the black hole. By the time you approached the horizon, you would be deformed, almost like toothpaste squeezed from the tube. There are two cures for tidal forces at a black hole horizon. Either make yourself smaller or make the black hole bigger. A bacterium wouldn't notice the tidal forces at the horizon of a solar mass black hole, but neither would you notice the tidal forces at the horizon of a million solar mass black hole. That may seem counterintuitive, since the gravitational influence of the more massive black hole would be stronger, but that thinking neglects an important fact. The horizon of the larger black hole would be so large that it would almost appear flat. Near the horizon, the gravitational field would be very strong, but practically uniform. If you know a little about Newtonian gravity, you can work out the tidal forces at the horizon of a dark star. What you will find is that the bigger and more massive the dark star, the weaker the tidal forces at the horizon. For that reason, crossing the horizon of a very big black hole would be uneventful. But ultimately, there is no escape from tidal forces, even for the biggest black hole. The large size would just delay the inevitable. Eventually, the unavoidable descent toward the singularity would be as awful as any torture that Dante imagined or the Torquemada inflicted during the Spanish Inquisition. The rack springs to mind. Even the smallest bacterium would be pulled apart along the vertical axis and at the same time squished horizontally. Small molecules would survive longer than bacteria, and atoms even a bit longer, but sooner or later the singularity would win, even over a single proton. I don't know if Dante was right in claiming that no sinner can escape the torments of hell, but I am quite certain that nothing can escape the awesome tidal forces at the singularity of a black hole. Despite the alien and brutal properties of the singularity, that is not where the deepest mysteries of black holes lie. We know what happens to any object unlucky enough to get pulled to the singularity, and it's not pretty. But pleasant or not, the singularity isn't nearly as paradoxical as the horizon. Almost nothing in modern physics has created greater confusion than the question, what happens to matter as it falls through the horizon? Whatever your answer, it is probably wrong. Michel and Laplace lived long before Einstein was born and couldn't have guessed the two discoveries he would make in 1905. The first was the special theory of relativity, which rests on the principle that nothing, neither light nor anything else, can ever exceed the speed of light. Michel and Laplace understood that light could not escape from a dark star, but they didn't realize that nothing else could either. Einstein's second discovery in 1905 was that light really is made of particles. Shortly after Michel and Laplace speculated about dark stars, Newton's particle theory of light came into disfavor. Evidence mounted that light was made of waves, similar to sound waves or waves on the surface of the sea. By 1865, James Clerk Maxwell had figured out that light consists of undulating electric and magnetic fields propagating through space with the speed of light, and the particle theory of light was as dead as the proverbial doornail. It seems that no one had yet thought that electromagnetic waves might also be pulled by gravity, and thus dark stars were forgotten. Forgotten, that is, until 1917, when the astronomer Karl Schwarzschild solved the equations of Einstein's brand new general theory of relativity and rediscovered the dark star. Black holes come in a variety of kinds. In particular, they can rotate about an axis if the original star was rotating. All stars do to some extent. And they can be electrically charged. Dropping electrons into a black hole would charge it. Only the non-rotating, uncharged variety of black holes are called Schwarzschild black holes. The equivalence principle. Like most of Einstein's work, the general theory of relativity was difficult and subtle, but it grew out of extremely simple observations. They were, in fact, so elementary that anyone could have made them, but no one did. It was Einstein's style to draw very far-reaching conclusions from the simplest of thought experiments. Personally, I have always admired this way of thinking above all others. In the case of the general theory, the thought experiment involved an observer in an elevator. Textbooks often update the elevator to a rocket ship, but in Einstein's day, elevators were the exciting new technology. He first imagined the elevator to be floating freely in outer space, far from any gravitating object. Everyone in the elevator would experience complete weightlessness, and projectiles would move along perfectly straight trajectories at uniform velocity. Light rays would do exactly the same, but of course at the speed of light. Einstein next imagined what would happen if the elevator were accelerated upward, perhaps by means of a cable attached to some distant anchor, or by means of rockets bolted to the underside. The passengers would be pushed to the floor, and the trajectories of projectiles would curve downward in parabolic orbits. All things would be exactly the same as if they were under the influence of gravity. Everyone since Galileo knew this, but it remained for Einstein to make this simple fact into a powerful new physical principle. The equivalence principle asserts that there is absolutely no difference between the effects of gravity and the effects of acceleration. No experiment done inside the elevator could distinguish whether the elevator was standing still in a gravitational field or being accelerated in outer space. In itself, this was not surprising, but the consequences were momentous. At the time that Einstein formulated the equivalence principle, very little was known about how gravity affected other phenomena, such as the flow of electricity, the behavior of magnets, or the propagation of light. Einstein's method was to start by first working out how acceleration influenced these phenomena. That usually didn't involve any new or unknown physics. All he had to do was to imagine how known phenomena would be seen from an accelerating elevator. The equivalence principle would then tell him the effects of gravity. The first example involved the behavior of light in a gravitational field. Imagine a beam of light moving horizontally from left to right across an elevator. If the elevator were moving freely, far from any gravitating mass, the light would move in a perfectly straight horizontal line. But now let the elevator accelerate upward. The light starts at the left side of the elevator, moving horizontally, but because of the elevator's acceleration, by the time it arrives at the other side, it appears to have a downward component of motion. From one point of view, the elevator has accelerated upward, but to a passenger, the light appears to accelerate downward. In fact, the path of a light ray curves in the same way as the trajectory of a very fast particle. This effect has nothing to do with whether light is made of waves or particles. It is just the effect of upward acceleration. But, argued Einstein, if acceleration makes the trajectory of a light ray bend, so must gravity. Indeed, you might say that gravity pulls light and makes it fall. This was exactly what Michel and Laplace had guessed. There is another side of the coin. if acceleration can simulate the effects of gravity, it can also cancel them. Imagine that the same elevator is no longer infinitely far away in outer space, but is instead at the top of a skyscraper. If it is standing still, the passengers experience the full effect of gravity, including the bending of light rays as those rays cross the elevator. But then the elevator cable snaps, and the elevator begins to accelerate toward the ground. During the brief interval of freefall, gravity inside the elevator appears to be completely canceled out. I am assuming that the elevator is small enough that tidal forces are negligible. The passengers float in the cabin with no sense of up or down. Particles and light beams travel in perfect straight lines. That is the other side of the equivalence principle. Drain holes, dumb holes, and black holes. Anyone who tries to describe modern physics without the use of mathematical formulas knows how useful analogies can be. For example, it is very helpful to think of an atom as a miniature solar system, and the use of ordinary Newtonian mechanics to describe a dark star can help someone who is not ready to plunge into the advanced mathematics of general relativity. But analogies have their limitations, and the dark star analogy for a black hole is flawed when we push it too hard. There is another analogy that does better. I learned it from one of the pioneers of black hole quantum mechanics, Bill Unruh. Perhaps I especially like it because of my first career, which was as a plumber. Imagine a shallow, infinite lake. It's only a few feet deep, but it goes on forever in the horizontal directions. A species of blind polywogs live their entire lives in the lake without any knowledge of light, but they are very good at using sound to locate objects and to communicate. There is one unbreakable rule. Nothing is allowed to move through the water faster than the speed of sound. For most purposes, the speed limit is unimportant, since the polywogs move much slower than sound. There is a danger in this lake. Many polywogs have discovered it too late to save themselves, and none has ever returned to tell the tale. At the center of the lake is a drain hole. The water empties out through the drain into a cave below, where it cascades onto deadly, sharp rocks. If you look down on the lake from above, you can see the water moving toward the drain. Far from the drain, the velocity is undetectably slow, but closer in, the water picks up speed. Let's assume that the drain draws off water so fast that at some distance, its velocity becomes equal to the speed of sound. Even closer to the drain, the flow becomes supersonic. We now have a very dangerous drain. The polywogs floating in the water, experiencing only their own liquid environment, never know how fast they are moving. Everything in their vicinity is swept along at the same speed. The big danger is that they may get sucked into the drain and then be destroyed on the sharp rocks. In fact, once one of them has crossed the radius where the inward velocity exceeds the speed of sound, he is doomed. Having crossed the point of no return, he can't outswim the current, nor can he send a warning to anyone in the safe region. No audible signal moves through the water faster than sound. Unruh calls the drain hole and its point of no return a dumb hole, dumb in the sense of silent, because no sound can escape from it. One of the most interesting things about the point of no return is that an unwary observer floating past it would initially notice nothing out of the ordinary. There is no signpost or siren to warn him, no obstruction to stop him, nothing to advise him of the imminent danger. One moment everything seems fine, and the next moment everything still seems fine. Passing the point of no return is a non-event. A freely drifting polywog, let's call her Alice, floats toward the drain, singing to her friend Bob, who is far away. Like her fellow sightless polywogs, Alice has a very limited repertoire. The only note she can sing is middle C, with a frequency of 262 cycles per second, or in technical jargon, 262 Hertz. The Hertz, named after the 19th century German physicist Heinrich Hertz, is a unit of frequency. 1 Hertz is the same as 1 cycle per second. While Alice is still far from the drain, her motion is almost imperceptible. Bob listens to the sound of Alice's voice and hears middle C. But as Alice picks up speed, the sound deepens, at least to Bob's ears. C gives way to B, then to A. The cause is the familiar Doppler shift, which can be heard when a speeding train passes while blowing its whistle. As the train approaches, the whistle sounds higher pitched to you than it does to the trainman on board. Then, as the whistle passes and recedes into the distance, the sound deepens. Each successive oscillation has a little farther to travel than the previous one, and it arrives at your ears slightly delayed. The time between successive sound oscillations is drawn out, and you hear a lower frequency. Moreover, if the train picks up speed as it races away, the perceived frequency gets lower and lower. The same thing happens to Alice's musical note as she drifts toward the point of no return. At first, Bob hears the note at 262 Hz. Later, it shifts to 200 Hz, then 100 Hz, 50 Hz, and so on. A sound produced very close to the point of no return takes an extremely long time to escape. The motion of the water almost cancels the outward motion of the sound, slowing it nearly to a halt. Soon, the sound becomes so low-pitched that without special equipment, Bob can no longer hear it. Bob may have special equipment that allows him to focus sound waves and form images of Alice as she approaches the point of no return, but the successive sound waves take longer and longer to reach Bob, thus making everything about Alice appear to slow down. Her voice deepens, but not only that, the waving of her arms slows almost to a halt. The very last wave that Bob can detect seems to take an eternity. In fact, it seems to Bob that it takes forever for Alice to reach the point of no return. Meanwhile, Alice doesn't notice anything strange. She happily drifts past the point of no return without any sense of slowing down or speeding up. Only later, as she is swept to the deadly rocks, does she realize the danger. Here we see one of the key features of a black hole. Different observers have paradoxically different perceptions of the same events. To Bob, at least judging by the sound that he hears, it takes an eternity for Alice to reach the point of no return, but to Alice it may take no more than the blink of an eye. By now you may have guessed that the point of no return is an analog for the horizon of a black hole. Substitute light for sound, recall that nothing can exceed the speed of light, and you have a fairly accurate picture of the properties of a Schwarzschild black hole. As in the case of the drain hole, anything that passes the horizon is incapable of escaping, or even of standing still. In the black hole, the danger is not sharp rocks, but the singularity at the center. All matter inside the horizon will be dragged to the singularity, where it will be squeezed to infinite pressure and density. When we are armed with our dumb hole analogy, many paradoxical things about black holes become clear. For example, consider Bob, no longer a pollywog, but now an astronaut on a space station, orbiting a huge black hole at a safe distance. Meanwhile, Alice is falling toward the horizon, not singing, there is no air in outer space to carry her voice, but signaling instead with a blue flashlight. As she falls, Bob sees the light shift in frequency from blue to red to infrared to microwave and finally to low-frequency radio waves. Alice herself seems to get more and more lethargic, slowing almost to a standstill. Bob never sees her fall through the horizon. To him it takes an infinite time for Alice to reach the point of no return, but in Alice's frame of reference, she falls right past the horizon and begins to feel funny only when she approaches the singularity. The horizon of a Schwarzschild black hole is at the Schwarzschild radius. Alice may be doomed when she crosses the horizon, but just like the pollywogs, she still has some time before being destroyed at the singularity. How much time? That depends on the size, or mass, of the black hole. The larger the mass, the larger the Schwarzschild radius, and the more time Alice has. For a black hole with the mass of the Sun, Alice would have only about 10 microseconds. For a black hole at the center of a galaxy, which may be the size of 1 billion solar masses, Alice would have 1 billion microseconds, or roughly half an hour. One could imagine even bigger black holes in which Alice could live out her whole life, and maybe even several generations of Alice's progeny could live and die before the singularity destroyed them. Of course, according to Bob's observations, Alice will never even get to the horizon. Who is right? Does she or doesn't she get to the horizon? What really happens? Is there a really? Physics is, after all, an observational and experimental science, so one would have to credit Bob's observations with having their own validity, although they apparently conflict with Alice's description of events. We will come back to Alice and Bob in later chapters after we have discussed the amazing quantum properties of black holes discovered by Jacob Bekenstein and Stephen Hawking. The drain analogy is a good one for many purposes, but like all analogies, it has its limits. For example, when an object falls through the horizon, its mass gets added to that of the black hole. The increase in mass implies that the horizon grows. No doubt we could model this in the drain analogy by hooking up a pump to the drain pipe to control the flow. Every time something falls into the drain, the pump would be turned up a bit, speeding up the flow and pushing the point of no return farther out. But the model quickly loses its simplicity. Professor George Ellis has reminded me of a subtlety when the flow is variable. In that case, the point of no return does not exactly coincide with the point where the water velocity reaches the speed of sound. In the case of black holes, the analogous subtlety is the difference between an apparent horizon and a true horizon. Another property of black holes is that they themselves are movable objects. If you place a black hole in the gravitational field of another mass, it will be accelerated just like any other mass. It can even fall into a bigger black hole. If we tried to represent all these features of real black holes, the drain analogy would be more complicated than the mathematics it was supposed to avoid. But despite its limitations, the drain is a very useful picture that allows us to understand basic features of black holes without mastering the equations of general relativity. A few formulas for those who like them. I've written this book for the less mathematically inclined reader, but for those who enjoy a bit of math, here are a few formulas and their meaning. If you don't like them, just go on to the next chapter. There won't be a test. According to Newton's law of gravity, every object in the universe attracts every other object, with a gravitational force proportional to the product of their masses and inversely proportional to the square of the distance between them. F equals lowercase m capital Mg over d squared. This equation is one of the most famous in physics, almost as famous as E equals mc squared, Einstein's famous equation relating energy, E, to mass, m, and the speed of light, c. On the left side is the force, F, between two masses such as the moon and the earth, or the earth and the sun. On the right side, the bigger mass is capital M, and the smaller mass is lowercase m. For example, the Earth's mass is 6 times 10 to the 24th power kilograms, and the Moon's is 7 times 10 to the 22nd power kilograms. The distance between the masses is denoted by d. From the Earth to the Moon, the distance is about 4 times 10 to the 8th power meters. This book is continued on Disc 2,